Calculation of density of states, in abbreviation DOS, is one of the important issues to find the electronic properties of materials. Many important material quantities and properties, such as electron or hole density, are calculated by using DOS. For example, these two formulas are used to calculate electron and hole density. DOS represents the number of electron states per unit volume per unit energy. If we multiply the DOS by the Fermi function and take an integral over the energy, the electron density is obtained. Thus, the calculation of density of states is important. DOS calculation needs 3 steps. The first step is self-consistent field calculation. We did it before. At the second step, by using non-self-consistent field calculation, density of states output file is created. And then at third step, we should plot this output file. This is the input file for non-self-consistent field calculation. It is similar to self-consistent field calculation with some change. For example, the calculation is changed to NSCF, that means non-self-consistent field calculation. NBND, that represents the number of bonds, is set to 8. Number of bonds equals to 1.2 multiplied by the occupied bond. Occupied bond equals to number of electrons divided by 2. We can find the number of electrons at the self-consistent field output file. Also, the occupation is changed to tetrahedra, and also we use higher density K point. To calculate density of states, we create a folder with DOS name and we put the content of self-consistent field files in it. To create an input file for non-self-consistent field, I use PWGUI graphical interface. We choose the non-self-consistent field in the calculation section. In the system section, note that we should select by ABC because we specify the lattice by ABC and not by seldom. In the system optional variable, we should define the number of electronic states or MBND. Indeed, we define the number of bands. It is calculated according to the number of electrons from self-consistent field results. NBND is set to 1.2 times the number of occupied band. Occupied band equals to half the number of electrons. To find the number of electrons, we can refer to the self-consistent field output file. To find this, we can see the self-consistent field output file. You can find the number of electrons here. Number of electrons equals 8. In our case, number of electrons equals 8. I set this value to 8. Also, we changed the occupation of state into tetrahedra. We should note that the address of input-output file and also pseudopotential file should be changed. Thus, in the directory, I define new address. New address for input file, new address for output file, and also new address for pseudo potential file. Then we go to the key points section. In this section, as I said before, we can use dense or high density key point, for example 24, 24, and then we save the file. Then we can see the input file for non-self-consistent field calculation. We can see the change. Calculation is set to non-self-consistent field. Also in the system section, number of bond equals to 8. Occupation is tetrahedra. And also we increases the key points. We use high density key points. Then we should run this input file. This is the second step. Click on run, configure and run. Now the calculation is over. We can see graphene non-self-consistent field output file here. After that, we should do third step. To do this, we should create an input DOS file. To do this, we choose File, New, New DOS.x input. We use the prefix name that we used before for self-consistent field, graphene SCF. This is the prefix name that we used for self-consistent field calculation. Then we define the address. After that, the minimum and maximum values of energies are required. -9 and +16. And then we should define a name for the final output file for dust calculation. For example, graphene dust dot dat. Then we save this file. This is our input file to plot the dust. To run this file, we go to the terminal environment. We write mpi run dust.x. Should write the name of input file and then the name of output file. As I said before, this is the input file for dust plot. You can see this file dust equals graphendust.dat. This file contains the values of dust. This file, graphendust.dat. This file contains the value of dust. To plot this, we can use many programs. For example, I use GNUplot. Go in terminal environment. I want to plot this file by using GNUplot. I type GNUplot. Can write plot, the name of the file, that is graphendust.dat with lines. Now you can see the density of state values over energy. Usually, we set the Fermi energy as the origin of axis. To do this, at first we should find the value of Fermi energy. If we look at this file, we can find that Fermi energy is this value, minus 2.276. And then in the terminal environment, I define Fermi energy, this value, and then I write plot graphendust.dat using. I want to set the Fermi energy as the origin of axis. Thus, the first column that contains energy should be minus from Fermi energy. I write $1 means the first column. I write $1 minus EF, and the second column with lines. Also, we can increase a little a line width with this comment. And now this is a density of states of graphene. From the graphene physics, we can see that around Fermi energy that is set to 0 in this figure, we can see that the density of state is near 0 around the energy of 0.